So once again, good morning everybody. Thanks to the organizers. Welcome to this lecture 1, which is basically Introduction to Epidermal and Subdermal Biosensing Devices. This is part of the GAN lecture series that we have here. Today is the 16th of June 2025. I'm going to be mainly giving you an outline on the epidermal and subdermal wearable devices. We talk about wearable devices. So we're going to be looking at what are these epidermal and subdermal wearable devices. This is the first lecture, so it's going to be more like an outline with some good examples. So don't worry if you miss out on anything. We will have multiple repeats, multiple examples which will be repeated so that we can make sure that the concepts get through easily and you can understand what epidermal and wearable device and subdermal wearable devices are. Now, as I mentioned this morning, subdermal wearable devices is 15 years of my life, so I'm basically giving you a summary of what I've done over those last 15 years, wherein I've taken the subdermal wearable devices from the lab into the clinic. So there's going to be a lot on translational research. So you'll see a lot of examples coming from my own research group, and I'll be happy to present them to you. This is the course structure that we have. As you can see, we are here. We've already finished the inaugural session. We are now doing this part here, which is basically 11:30 to goes on from 11 to 12 or 11:30 to 12:30 as it says on the calendar. Today's day is mainly on introduction to the devices, and then we'll have an afternoon session where we will talk about the basic principles of electrochemistry which are relevant to the biosensing technologies. The learning objectives of this particular lecture is mainly to understand the fundamentals of epidermal and I say microneedles. I'll use microneedles as less as possible because there are a lot of people who have needle phobia. So I try to use the term, I try to substitute the term microneedle with subdermal devices. But when I say subdermal devices, meaning devices that sit a bit under the skin, what I'm meaning is microneedle devices. Right? I mean, if you look at these devices and if you feel these devices, you don't feel any pain. But anybody who imagines those things, they always think that this is something that's got a needle in it and it's going to give you a lot of pain. I mean, in reality, they sit far away from your nerves, so there's not going to be any pain at all in these particular devices here. We're going to be looking at applications, we're going to be looking at examples, plenty of examples, and then we're going to discuss the challenges and the future directions, and I'm going to show you some real examples from the real world of research. Some of them have also made it commercially to the market as well. I think we might have a few CGMs sitting around which we might be able to present to you if need be. We'll try to do that during the workshop. Suggested reading, I mean, you'll be getting a copy of these slides. My suggested readings would be two of these papers here. Both of these papers have come out of my group. One of them is on wearable technology, which is for One Health. It is charting the course of dermal biosensing. It includes both epidermal and subdermal wearable devices. And the other paper is Lab on a Chip. You don't need to take any notes on these papers. You will be getting the DOIs of these. And I think these are all in the open access section, so you can easily download these papers and read them at your own leisure. Now let's start off first of all with what are wearable sensors. So in the morning session, you heard about wearable devices. Anybody here with an Apple Watch or a watch that measures your steps? 1, 2, 3, 4, yeah, many people. So, I mean, this has now become the latest fashion, right? People don't like those gold Rolex watches. They all like to use the smart watches, as we call them, which are normally paired to your smartphones. Now, these smart watches or these wearable devices, I mean, that's a classic example of wearable devices. These wearable devices are actually looking into physical parameters. They have accelerometers, they have motion sensors, they look at the way you walk, how many steps you've taken. And some of them are even capable of measuring your heart rate using surface acoustic waves. Yeah, some of them can even give, if you have an Apple Watch, the latest one, it can even give you an ECG if you want it, right? So you have these wearable technologies which are actually taking a fantastic, they're following a fantastic course. But the examples or the areas where you can apply these wearable technologies is very limited. I mean, you're mainly looking at well-being side of things. We would like to take these devices from the arena of well-being into the area of more kind of clinical applications. Can these be used for prognosis or for early diagnosis of, for example, epilepsy? Can these be used for brain infections? Can these be used for neurodegenerative disorders? So these are the type of questions that we'll try to answer through this whole series, the GAN lecture series that we have. So wearable devices, as the name suggests, are devices which can be worn and which can give you real-time information. I mean, because they're monitoring continuously, so they monitor your health in a continuous manner, so they are real time and they're continuous health monitoring devices. And what are they based on? So, I mean, the ones that we are going to be focusing on, the epidermal and the subdermal ones, they are going to be utilizing, or they are going to be basically detecting molecular markers in biological fluids such as sweat and ISF. Anybody here who knows what is ISF? Yes? Skin interstitial fluid, right? So, what is skin interstitial fluid? Skin interstitial fluid is the fluid that you have between the cells, right? What is the nice thing about skin interstitial fluid is that the skin interstitial fluid, the volume of the skin interstitial fluid in the body is 2 to 3 times more than that of the blood that you have. Now, if you have to tap into blood, which is the easiest form of blood you can tap into? Capillary blood, right? So, you might have seen people who manage glucose, right? They have a glucometer. They take a lancet, they prick the finger, get a drop of blood, that's transferred to a strip. Again, that's biosensing technology there, working at its best, right? We'll have some lectures on that as well, because I've got some nice pictures there as well for you. So, that's capillary blood. But if you were to access venous blood, can anybody here sitting in the crowd access venous blood? I mean, capillary blood, we already know it's being accessed in home conditions. You know, diabetics, type 1 or type 2 diabetics in home conditions would prick their finger, draw a drop of blood, and they can measure the in capillary blood. Then they know that there isn't much, there's pain there. I wouldn't say there's no pain, there's pain there, but you can measure. You don't have profuse bleeding after that, right? That's not the problem with capillary blood. With venous blood, can you do it with venous blood? No. So, if you want to measure something in a minimally invasive manner or a non-invasive manner and has to be done in real time continuously, what's your best sample fluid there? It's either sweat or interstitial fluid, right? Again, I say all of these, just have to remember one thing, no one technology is better than the other one. They're all complementary. Some technologies have got their own pros and cons, other technologies have got their own pros and cons. So, please do not even imagine for even 1 second that epidermal biosensors is the solution for all the real world problems, or subdermal sensors are the solutions for all real world problems. And you will see that through this whole series that we have here. So, we are going to be looking at mainly epidermal sensors, epidermal biosensing devices, which measures, when I say epidermal, so you have the skin, you have the epidermis. When I say epidermal, it means something which is on the surface of the skin. You know, your sweat normally is produced by the body through the sweat glands, and it comes on top of your skin. So, that's the epidermal devices. And then we will be looking at subdermal here. I've also used the term microneedle just to make it a bit more clear that then you are disrupting the stratum corneum layer and going a little bit down there. If you haven't understood stratum corneum, don't worry, I have plenty of pictures of microanatomy of skin, and I'll make it clear as we go into it. So, we're mainly going to be focusing on epidermal and subdermal formats here. And what are the sensing mechanisms? The sensing mechanisms would be the standard mechanisms that you would find in a biosensor. For a biosensor, you would have heard about electrochemical, and there's a second format as well. In fact, there are multiple formats. Can anybody give me another example of a biosensor which is not electrochemical biosensor? Optical, right? Where you look basically looking at optical signal transduction there, right? You're looking at whether it's absorbance measurements, whether it's fluorescence measurements, there are different formats there. But most of the wearable devices that we're talking about, especially my research has been mainly in the area of electrochemical biosensors. So, this whole GAN series will focus on the electrochemical sensors here. And we'll be looking at the different electrochemical methods. You could be using looking at amperometric sensors, you'll be looking at potentiometric sensors, you'll be looking at voltammetric sensors, and then you'll be also looking at different bioreceptors. Now, you need to understand, when you talk about a biosensing device, at the heart of the biosensing device is a bioreceptor. Why do you need a bioreceptor? Because the bioreceptor is your molecular recognition element. Glucose sensor is glucose sensor because it's very specific to glucose. You need to understand whether it's if you look at any biological matrix, whether it's whether it's blood or whether it's sweat, or even for that matter it's skin interstitial fluid, it's a complex mixture. It will have a lot of endogenous and exogenous products. Blood will have a lot of proteins in it. Yeah, you might have heard about albumin, right, which can easily go and clog the sensor surface. You need something on your sensor which gives it the required specificity. That's where your bioreceptors come in. We'll be talking a little bit more on the bioreceptors and the mechanisms in the following slides. Bioreceptors that you would see normally are enzymes, aptamers, and antibodies. These are the most commonly used bioreceptors. The ones where you use enzymes are called as enzymatic sensors. The ones which use aptamers are called as apta sensors, and the one that use antibodies are called as, feel free, there's no wrong answers, come on, immunosensors, right? So, you have immunosensors. And then the signal transduction will depend on the analyte properties. What kind of analyte do you have? That decides the signal transduction. Let's have a look at the underpinning sensing mechanisms. You have 1, 2, 3, 4 and 5 different schematics here. If you look on your screen, the first one is the conventional sensor where you see there's an electroanalyte. It comes in, reacts with your target molecule and gives a byproduct, and that particular reaction is then seen in the form of a signal transduction. Another example is that of an ion selective sensor. If you want to know more about it, your Professor Khalid has got some work going on. I think he works on cationic sensors. He works on potassium and sodium. Normally what you do here is to have the selectivity. You normally have a selective agent, and then you basically coat your working electrode with it so that it becomes selective to your ions. It gives you the desired charge and size, and that's how you normally do the measurement there. And the third one is an example of enzyme sensors. This is your classic example is glucose sensors. I mean, everybody loves glucose sensors. Glucose sensors are so much loved that they form nearly 80 to 85% of the whole diagnostics market is glucose sensing. And the other reason is because we have an epidemic going on, which is your diabetes. I mean, diabetes is a major issue. Earlier it was a problem with the Western world. Now it's a problem in countries like India. I think people do not complain when they get late to the hospital, when the ambulance is late, but people complain when the pizzas get late, right? This is we, as they say, we are all victims of our own success. We've all now got enough disposable income that we've started eating a lot more junk food, and that's what is leading to this increase in the problem of diabetes. The next example you have is that of an antibody sensor, which I also referred to before as the immunosensor. As you can see here, you've got the antibodies, which are in the shape of the Y-shaped structures, which bind very specifically to your analytes of interest. And there you can see that the electron transfer has been blocked. So you will see some changes in the electrochemical property, which is then seen or measured in the external circuit. And last but not the least is your apter sensor, which is based on aptamers. Aptamers are basically strands of oligonucleotides. We all know your oligonucleotides, or everybody understands the double helical structures. You have bases which are complementary. They bind. There's very specific interactions. Not only do they bind to bases, they can also bind to molecules. And again, they use the whole principle, and that specificity is also very high. And we'll be talking about terms like selectivity and specificity as we progress, because that's very important that you need to understand. Okay, so this will all come through as we go through the lecture series. Let's now look at examples of epidermal sensors. Now, before I start on epidermal wearables, let me tell you, this is not my area of research. The reason I'm presenting this is something that that Professor Khalid and Dr. Prasun are planning to venture into. So this is something that will probably, the activities will start in NIT Rourkela. I myself am looking into it, although I'm very happy with my subdermal sensors. But as I said, these are complementary sensors. So if you cannot get good answers, or if it's hard to access the biofluid using one technique, then you can use the other technique, or you can use the other biosensor. So we'll stick now to epidermal wearable sensors, and I'll give you examples of epidermal wearables here. As I mentioned to you before, epidermal is something, when you talk about an epidermal wearable device, something that can be like a ring, right, sitting on top of the surface. Anybody here heard about the gluco watch? Yes. What does the gluco watch do? Brilliant answer. It uses reverse iontophoresis to extract the sweat out of the body, or the interstitial fluid out of the body, and it measures in that particular thing, right? So very interesting thing. And the reason the gluco watch failed was not because there was a fault with the technology. Absolutely, bang on, fantastic. You're a PhD student, I believe. Fantastic, good research there. So yeah, I think you can use the microphone. I mean, she's loud enough. I can hear her. Maybe recording can't this thing. So this is the problem here. Is that when you talk about technologies, you need to look at every aspect of the technology. So there's nothing wrong with. And do you know where the gluco watch came from? Which university did it come from? It came from University of Strathclyde, from Patricia Connolly's group, right? She gave a keynote lecture in the 2010 World Congress on Biosensors, and that's where I heard her speak about it. Very unfortunate, a fantastic piece of technology, but it failed because the tolerability or the acceptance of the technology was very poor. People would have the technology. Imagine you have a technology, which is a fantastic technology, giving you all the information that you need. But the reason is that, this morning we also had heard it from Professor Sahu as well, when he said about, you need to go back to the drawing board and then redesign this thing. The problem there was the adhesive that was used for sticking these technologies onto the skin surface was actually giving bad allergic reactions. Therefore, the technology had to be abandoned. And that's how it had to be pulled out of the market. So epidermal wearables, again, We are talking about thin, flexible, conformal devices. When I say conformal, something that will conform to the size. If it's a finger, everybody has got different shape and size of finger. It should be something that nicely conforms to your skin, and that can be worn on the skin. And what does it do? It will detect sweat-based biomarkers, examples being glucose, lactate, and cortisol. Now, the first two fall in one category of biomarkers. The second one is a different biomarker. Can anybody tell me the difference between glucose and lactate and cortisol here? I'm just making you think about what I'm saying here, and most importantly, I'm keeping you awake, because if you fall asleep, I'm going to fall asleep. Yes, glucose and lactate, these are bioproducts, these are metabolites, very small molecules, right? And when you talk about cortisol, what is cortisol? It's a stress hormone, right? Do you expect the size to be the same, falling in the same category of glucose? No. So it's a stress hormone. So it's produced by somewhere in the skin, some gland in the skin, right? Skin is an amazing organ, right? I call it a treasure trove of biomarkers. Skin is the largest organ in the body, right? With the exception of your bottoms and your feet, the skin is the same everywhere. So you can imagine the plethora of opportunities you have in your body to have a sensor inserted or implanted, right, if you want to monitor in the skin. All right. And you can use epidermal wearables when you want to do non-invasive, and you can use it for tracking well-being, right? So glucose and lactate are examples of well-being. Glucose is normally produced, you burn glucose, low glucose levels, good or bad? Bad? You can faint, but that's what levels are we looking at? I know there are a lot. The reason I'm saying this is I'm trying to standardize the whole class, because I know there are also some engineers sitting here. So we need to also start looking into things like concentration here, right? Something that I appreciate more than Khalid. Khalid is somebody who is more an engineer. He would just make things and say, oh, the electronics works very good. I've given you a signal amplifier. That should be fine. And I'll be looking at, no, the signal amplifier isn't amplifying the signals to give me enough sensitivity that I require for my analyte here. Glucose, what's the normal concentration of glucose?
70 to 120 milligrams per.
Yes, I mean it depends on the unit that you use. So 65 to 110 mg per deciliter is what was used to be the standard. Now they're changing it because they know that it's very hard to maintain that unless you have black coffees every day. Okay, so glucose, that's this one, and also in terms of millimole per liter, it's about 4 to 6 or 4 to 7 or 4 to 8 is what the desired range is. So when you say low glucose, you're talking about hypoglycemia. Hypoglycemia is bad. Hypoglycemia can be lethal. A person can go into coma and probably might come back or might not come back. So hypoglycemia is lethal. But the other thing that's the killer is the hyperglycemia. The problem with hyperglycemia is that over a period of time, it doesn't happen instantly. That's the reason it's less dangerous than the hypoglycemia. When your sugar levels stay in the above the normal range for a very long time, they start creating these different pathies that you normally hear about. They cause problems with the heart, which is called as the cardiomyopathy. They cause problems in the eye, which is called as retinopathy. They cause problems with the kidney, which is called as nephropathies, right? We all are I'm not a medic myself, but if you want to work in the area of wearables, a multidisciplinary area, you have to start familiarizing yourself and start using terms and speak as if you're a doctor yourself, right? I may sound like one, but I'm not. Okay, so epidermal devices are basically non-invasive devices, and they're suitable for tracking the wellness. Okay, here's the first example of an epidermal device. This was some work that was published in 2018, and here is the work done by Hong et al., where you can see what he's got is he's got this sweat strip glucose. If you look, what he's done is he's got something similar to like a glucose watch thing. He's got a strip that's inserted. He's done the dry. He's got it dry, and then it absorbs the sweat, goes into a wet state, and then he's measuring on that, and then you have the data integration using a PCB-based circuit that's there. I think this is something that we will discuss more when we have the lecture from Professor Khalid. And as you can see here, he's measuring glucose. You can see the electrochemical data. That's the typical chronoamperometric curve that you see on the top there, and then you can see what is happening pre-exercise blood glucose and your post-exercise blood glucose, and also the physiological data. So they also have some accelerometers and stuff like that. So they're giving you both information on the molecular markers, which is your glucose, and also the physical parameters, which is how many steps you've done, and in response to the steps, how does your glucose. That looks really neat, right? When you have number of steps and your glucose dropping down. That's giving you good information, and that's the kind of information that you need. It not only gives you that, it also tells you about the heart rate, it also tells you about the blood oxygen levels, and it also tells you about the physical activity. So that's a first example wherein you have a wearable device combining molecular markers with your physical markers that was produced in 2018. It's been some time now. Let's have a look at the second example here. This work came last year in 2020. This is a sensing platform, which is again a fingertip passive sweat treatment. So you're taking, similar to a capillary blood, you're taking a small drop of blood from your fingertip, and you basically transferring that onto what looks like a screen printed electrode. The one which shows the scale bar of 1 centimeter. You're using that, and then you're using that to look at different types of biomarkers here. You're looking at glucose and ketone bodies. Glucose is a good biomarker of wellness, of well-being, right? High glucose values, as long as you're in the normal range, it's all good. You can get high values in response to a bolus, which means when you eat something, you have a postprandial peak. That's all fine, right? But it should come back immediately, and that's a good sign of a healthy pancreatic function there. All right. So, and you can see here there are some on this one. You can see there are 2 of these mechanisms here. We will cover this. Don't be scared with these mechanisms. They're basically showing how you have glucose. You can see this one here, glucose oxidase. So what's happening here is glucose is coming. You have your glucose oxidase, which is an enzyme, right? That's what's giving it the required specificity. Glucose oxidase itself is oxidized to gluconic acid, and this then reacts with the oxygen and then generates hydrogen peroxide, and then you have your Prussian blue, and that there's this whole cyclic thing that goes on there. The good thing, when you see these kind of cycles there, it's a good thing, right? That means that your target analyte or your bioreceptor is not being consumed, right? It's being regenerated. So it goes from the oxidized state to the reduced state, and then reduced state back to the oxidized state. So you can see there are 2 cycles here, 1 cycle and 2 cycles which are being driven, which drive each other, and that means that you don't need to keep on replenishing your keep on replenishing your bioreceptors there. So that's a very neat way of doing things. Similarly, down you can see this is the example of ketone sensors. I think this is some work that's being again started at your own campus by the 2 gentlemen here, Professor Khalid and Professor Prasun. This is on using hydroxybutyrate, which is HBD, which is used for monitoring ketone. Ketone is again another metabolite, which is basically an indicator of stress. A lot of monitoring is done in cows, so if you have any collaborations with veterinary school, you would want to measure these in cows as well, because in cows it's a good indicator of stress hormones. This was some work which was published by Sempianato in 2020, and the paper is called the fingerprint. I think this is an ACS Sensors paper that was published in 2020, which I think you will find very interesting as well. So another example of epidermal wearable devices here. The only thing, the problem I have with this device here, it's been sold under epidermal wearable devices because it comes from the group of Professor Joseph Wang. I think he's one of the pioneers in this area, but I think the problem I have here is this is not something that you're wearing conformally on top of your on your finger. It's something wherein the biomarker is basically being transferred from your fingertip onto a screen printed electrode. Okay, another example here. This one I would definitely call an epidermal wearable device. What do you say? Yeah, this is where it's been worn on the body. You can see the device itself is made of multiple layers. You can see that you have a top layer which has got all the electronic and the wireless. So people who are working on bioinstrumentation side and with Professor Khalid, but should be able to should aim for making something as small as these, wherein you have your electronic and wireless all integrated on a single patch. That then goes to a microfluidic platform, and your microfluidic platform basically does the distribution of your sample. So you have your sample going in here, and then you can distribute it into different reservoirs, or you can bring in the reservoirs to bring in other reagents. You can do the mixing, and then you can do the measurements. As you can see, the measurement is normally done towards this end here, and underneath that you can see are the different working electrode, counter electrode and reference electrode, which should basically do the electrochemical detection of the devices. Now this is a device which is again an epidermal wearable device which is used here for measuring cortisol. Okay, so cortisol, and this is also measuring in sweat. So it's also telling you, it's also doing some bioimpedance measurements and telling you when the sweat levels are going up, and then also measuring the cortisol levels, so that you can get an idea as well. Because one of the problems you have with sweat is that you don't produce sweat uniformly throughout the whole day unless you're sitting in the same environment. So that's another challenge that you have here when it comes to epidermal sensors here. And then this is another example here. This is a wearable sweat device, and this device was developed by E et al. This is basically published in Nature, and this is where they have done some real-time determination of this is more for female health, reproductive health. This is a particular hormone called as estradiol, which is basically measured in sweat, right? So you can see this is a estradiol hormone here, which is normally, and this is a nice little tiny piece of thing. Imagine you can measure these things on the skin, right? Gets rid of all that things that you have to go and, you know, and especially if you're doing continuous monitoring, right? So what happens is our body is a very, very complex machine, right? When it comes to hormones, and I'm not, whether it's females or males, many of these hormones are produced in a very cyclic manner, in a pulsatile manner, right? So if you're doing point measurements, right, for example, pregnancy test kit, if you have a kit similar to a pregnancy test kit, that's more giving you a point measurement, right? It's not giving you, for example, a blood glucometer. That's a point measurement, right? And if you look at the way your blood profile changes over your day, so you get up in the morning, you have a certain blood glucose level, your body, your pancreatic cells are producing basal insulin, and then it gives it a bolus as well. Your sugar levels drop accordingly, and then you basically have a bolus, or you have some food in the morning, your levels go up and then they drop down depending on what you eat and how your body metabolizes it. So it's a continuous profile. You need to know, when you look at the profile, there's a lot of information in terms of the direction, the duration, and the changes in magnitude, where it's going from low to high. If you go to a clinician, he would like to look at the full picture, because we are all heading towards what we call as personalized healthcare, right? Everybody is different, right? If I'm getting a shot of insulin in response to because my bolus isn't going down, and that might be the way my body is reacting to it. So I should know what my profile looks like. What does my typical profile looks like? And that's why this whole market of continuous glucose monitoring devices are available. Similarly, in the case of hormone, that the reason I give you this example is just to make you understand that there's a lot of information in terms of the direction, whether it's going up or down, the duration, how long does it stay up, and the magnitude of changes. And those can only be captured if you have something which is more continuous, something which can give you real-time information. So these epidermal wearable devices give you that kind of information, wherein you can measure things in the sweat. Now here the challenge is, how do you make a person sweat for the entire duration of the day, right? Especially making somebody sweat during the night time. Is it possible? So that's a thought for you to think about. How useful is sweat as a sample, as a biometrics? Okay, that also reminds me the example of anybody here remembers the Google contact lenses? Remember that? Did that go anywhere?
No.
No? Why not?
I think the tier.
Sorry? Tears. It relied on tear fluids. What else?
No, sir.
So what is the challenge?
I think the challenge was that the correlation between blood glucose and the glucose that is present in the tears.
That you've become very technical. That I would take that. But that will be reason number 2. What is the reason number 1?
Lack of secretion, continuous secretion, I guess.
These continuous monitoring sensors, they are meant to aid the user. When does a user need to help them the most?
Before
when
food,
they're in sleep.
Yeah.
Can you imagine wearing contact lens and going to sleep? How many people here wear contact lenses? I mean, fine, if you don't have to. Is it easy or is it convenient wearing contact lenses in there? So the whole idea of using contact lenses during your sleep, it seemed to be very flawed right at the start. Khaled, you're giving the answers because you know the technicality of side of things, but the real reason is it's a product that I think, as mentioned by Professor Sau, it's a product that needed to be redesigned, and of course then it never went anywhere ahead. Okay, let's move on. Here's another example. This is an example of a colorimetric sweat biosensor. This is not an electrochemical one, it's a colorimetry, meaning that this is something where you see color changes, right? This is an example where they are basically looking at kidney function, right? So they're looking at biomarkers, they're looking at things like electrolyte imbalance, they're looking at inflammation, and this is something published in the American Chemical Society journal by Mishra et al. And this is a recent one actually. This is not that long. It's 2022 paper, wherein basically they've got an inlet chamber. They're looking at kidney function. They're looking at fitness, electrolyte imbalance, and they're also looking at inflammation. So this is an example, a little bit away from electrochemical. This is more an optical one here, wherein again you're tapping into collecting sweat, and then you're transferring the sweat using a microfluidic system into 4 different chambers, and then you're looking at the different color, and based on the color you're making an assessment. This is more simple to those urine strips that you have, wherein you can look at the pH and stuff like like that and see if there's an infection or not. That's a very crude way of doing things, but a very convenient way of doing things as well, right? If you can get information this way. I think this is also an ACS Census paper here. So those of you who are planning to publish in journals, ACS Census is one of the papers, is one of the journals which is definitely looking for papers which is on biosensing devices. This is another one which is a wearable lactate which has been powered by a biofuel. This is where you're kind of bringing in together two different areas. You're bringing in the whole area of biosensing combined with biofuel cells, because I think there's some interest which has been shown by Dr. Prasann and Professor Khalid on trying to have these biofuel cells integrated there as well. So some people talk about harnessing the glucose that you have to run biofuel cells. You can use that. It's a fantastic device, right? A self powered device which is running on the glucose in your body and measuring glucose as well, or measuring other analytes like lactate and stuff like that. So this is a classic example wherein they've combined a wearable device with another technology which is the biofuel cell, and since both of them can be miniaturized, you can easily get these devices there. Okay, these are again sweat sensors. These have been used for sweat pH, looking at the pH of your sweat, ascorbic acid and lactate. As I mentioned, lactate is a biomarker of stress. Yeah. Now we move to the next part. Again, I've used microneedles here. Now I'm going to be a bit more enthusiastic. If you found if my enthusiasm was a bit low in my last section, it's going to go higher now, because this is something which I talk very passionate about, and this is my own 15 years of summary which is on microneedle based sensors, which I would actually like to substitute and say these are subdermal devices, right? I mean, everybody has got a right to kind of name their devices. I mean, we started off the whole journey of microneedles calling them different things. We were calling them microspikes because our clinicians with whom we worked, they didn't like the word needles, so we had to use microspikes. We had to go back to microneedles because the publishers were giving us a hard time. They said, microspikes, how can you introduce new terms? So we had to go back to microneedles. Now, because we have established ourselves, so now people are listening to us, so we are now looking into using the term subdermal based wearable devices, because what happens is the whole process of product development involves something called as PPIE, which is basically called as patient and public involvement groups. So when you work with clinicians, the clinicians have got groups. Like if you're talking about finding solutions wherein you're looking at continuous glucose monitoring in children, when you go and speak to a child, right, or you have to talk to the carer first. You need to understand what the problems are. The carer will ask you, okay, so what does this device do? If you say this is a microneedle based device, the moment they hear needle, even they wouldn't understand, they wouldn't have even seen it, they say, no, I don't want it, right? So you want to get more and more people involved without sending the wrong messages. So you need a term that captures it nicely. You just say it's a wearable device, right? And later on you can go into the details, because how much does it matter whether, as long as it's performing its function, how much does it matter to a child whether it's measuring, it's an epidermal device or a subdermal device or a microneedle device or and I'll show you pictures. I've got pictures of microdialysis and suction blisters which look very, very horrible. And those are also ways in which, when there's a need for that, you have to do that as well. Those are traditional methods by which you can extract out the skin interstitial fluid out of the body, right? So we're going to be focusing in this particular section on the subdermal wearable devices. I think we are okay for time right now, because the next section, I think we might fly a little bit here. Now, when I talk about microneedle or subdermal wearable devices, we're talking about devices that will penetrate the outer layer of the skin and access your skin interstitial fluid in a minimally invasive manner. Okay. Now, what happens is sweat when it comes above the skin. Skin interstitial fluid stays underneath. You need to understand that you have the skin interstitial fluid which is in constant equilibration with your venous blood through a layer of subvascular plexus. I'll be showing you some slides which will come through. These will enable more stable and reliable biomarker tracking. You can get real-time information because, that volume doesn't change. You're not extracting out anything. You're mainly looking. You can extract it out, but you're mainly sitting there and you're measuring things. And as I said, the volume of skin interstitial fluid in the body is 2 to 3 times more that of your blood. Right? If blood in the volume of blood in the body is 5 liters, you've got 12.5 liters of skin interstitial fluid in your body, right? And then you can imagine the skin, the largest organ there as well. And this particular monitoring, these devices are suitable for monitoring of metabolites such as glucose, lactate and ketones, and also hormones, stress hormones, and also hormones which are related to different other endocrine and endocrinology applications. Let's go delve down a little bit into this area of microneedle arrays. So I started working on these from 2010. Thanks to Professor Tony Cass, we had an NIHR project from 2013 onwards, but this is where we got some clear directions from Professor Tony Cass, one of the visionaries. I'll show you his picture later on. Still continues to be my guru. I started working on this area of microneedles. This is something, and this is nothing new there. This has been there since 1970s. I think there have been some MEM labs, when they were doing silicon fabrication and they started making all these fancy IC integrated circuits and stuff like that. So they said, why don't we use these high throughput scalable technologies to make silicon based microneedles? So they've been there for a long time. So they've been there from 1970s. They come in different shapes and size. And the real applications when they started were more on delivery side of things, right? They were mainly used for delivering drugs through the skin, right? Because transdermal, anybody understands transdermal? Where you have ointments, you have sprays and things like that where you apply, that's transdermal. The problem is you have a thick, I wouldn't say a thick layer, you have a very robust layer of stratum corneum, a layer of dead cells under your skin in your epidermis, which actually acts as a fantastic barrier, right? Which actually makes your skin waterproof. Otherwise, everything, it will just, it will just kind of dissolve in the water if it wasn't waterproof, right? So that stratum corneum layer needs to be broken down, because if you don't break it down, there's only 20 drugs that can be actually administered transdermally, right? So to increase the number of drugs that can be administered transdermally, the whole concept of microneedles was introduced. Because when you imagine you take drugs through your alimentary canal, through the through the enteral route, through your intestine, you have the when it goes through the hepatic pass, a lot of drugs are metabolized there. You lose a lot of drugs there. So it's very important that the drugs are given through other routes which increase the bioavailability of the drugs, because a lot of drugs get metabolized when they pass through your alimentary canal. You have to then use you end up using drugs, high levels of drugs there, so that and some of the coatings that are used are not the best coatings, are not very not very good for the alimentary canal, for the digestive system. You might have heard about aspirin, how these drugs go and cause things like ulcers in the stomach and stuff like that. So those are problems, and to overcome these problems, microneedle arrays were introduced as real, and the real applications, as I mentioned, were drug and vaccine delivery. And there's also this nice image, 3 images here. All these 3 images are from my own work, wherein as I said, I've been working on this from 2010. The first one is where you had photolithography, which has been used. We were working in the clean room. We had a fantastic, expensive clean room. We call it as the white elephant of any institute. You can make fancy things, but it's got very high maintenance cost in making them. These were made one wafer, 6-inch wafer, quartz wafer in a week, just getting one of these ones, because you're looking at 1 millimeter height. The second one is an example of electric discharge milling. This was a workshop that we had in our physics department, where we are electric discharge milling. Here I was using the molds, which are made up of aluminium, and basically making about 50 of these devices in a week. And then we moved to the final one, which is injection molding. Injection molding is a fantastic technology. It is a highly scalable technology. Now we make our biosensors, we make our microneedle platforms out of injection molding. And the nice thing here is you can make polycarbonate. Price of 10 pence, you can make thousands of these injection molded devices. That's how cost effective and how scalable this technology is. And these are examples of work that have been taken from my own work from Imperial College. As I said, they come in different shapes and sizes. They come in different formats. They could be solid microneedles, again for drug delivery applications, wherein you coat them. You can coat them. You can have dissolving. You can have hollow microneedles. You can have swelling. I mean, these are things more related to drug delivery, so I won't spend too much time on these. What these basically do is they go and puncture the skin, create a little conduit there, and create a drug reservoir, and the drug then sits in there and then slowly diffuses through the different layers and goes into your subvascular plexus and then enters into your systemic circulation, and that's how you have a high bioavailability there. They are promising devices. They've been used for painless delivery of drugs. As I said, they give you a high bioavailability, and they've been suggested for things, highly specialized therapies such as immunotherapy. Anybody here understands immunotherapy? These are therapies that are normally given in response to disease, even treatment of cancer and stuff like that. So there, because you have the skin, which is your first line of defense, so you have your immune cells there. So therefore, they have been suggested for immunotherapy as well. And this is a nice picture taken by my PhD student at Swansea University, where she's shown these microneedle arrays, where you have these microneedles of different sizes. And as you can see there, they're made up of silicon. And this is where she's mounted it in the front of a syringe. And she's showing how you can push drugs through, but you would never do that with the skin, otherwise you can easily tear the skin apart, right? This is just to show you proof of principle that you can actually push drugs through there. You'll be using something more gentle there, otherwise imagine using a syringe there. That defeats the whole purpose of using microneedle arrays there. All right, I'm just going to quickly go into skin anatomy and a bit of sensor integration. The skin basically comprises of different layers, epidermis, dermis and subcutaneous layer, and there are two different models which explain the biomarker distribution in the skin compartment. One is a two compartment model wherein which basically explains you that you have the subvascular plexus and there's the equilibration going on there, and the other one is the ectodermal origin theory. I have figures to show you for those of you who are interested in understanding what explains the presence of biomarkers in the skin compartment, because it's very, very important that when you look into a clinical application, you might meet a clinician who says, oh, I'm actually looking for a biomarker for example, Alzheimer's. Now Alzheimer's, what are the biomarkers there? You've got p-tau proteins, you've got the amyloid proteins. Are these actually present in the skin? Is there enough evidence there? How can they be present in the skin? Then this is where you apply these two different theories. You apply the biomarker distribution models. It comes in the next few slides. And then, as I said, because your skin interstitial fluid is in constant equilibration with your subvascular plexus, and through the subvascular plexus with your venous blood and your capillary blood and your arterial blood, it's basically a treasure trove of biomarkers, and it closely resembles the blood chemistry. As I promised, here are the different images. Let me get all the images together here. So as I mentioned to you, the skin is a treasure trove of biomarker, the largest organ in your body. It's got different layers. You've got your epidermis here, you've got your dermis, and then you've got your hypodermis. We are not concerned about the dermis. We are mainly concerned about this region here, the epidermis, and this fine layer that you see here, the dark line layer that you see here, is your layer of dead cells, which is called as the stratum corneum layer, right? So when you have this, and the fluid that bathes the cells here is called as the skin interstitial fluid. And what you see here, this one is your subvascular plexus. The subvascular plexus are very fine capillaries. They're finer than capillaries that you see in your fingers. And these are actually in constant equilibration with your blood vessels here. And you have your sweat glands. The sweat glands are producing the sweat that you will be using for your epidermal. So what you need to understand, the route of which your biomarkers are actually coming on the surface of the skin is different. There, in this case, it's coming through your sweat glands. So you need your biomarkers to diffuse from the skin compartment into your sweat glands and then be excluded or be released through the body, released through the sweat gland on top of the skin surface, and that's where you bring in your epidermal cells. The subdermal sensors is where your sensors are actually monitoring in your skin compartment, within your skin compartment, sitting in the space between the epidermis and the dermis. That's what we call as the subdermal one here. As I mentioned, a lot of skin interstitial fluid, a wealth of information here. You can extract skin interstitial fluid in different ways. You can use microdialysis, you can use suction blisters, right? Problem with microdialysis, anybody here seen microdialysis, heard about microdialysis? Khalid, did you have any microdialysis done when you were at Imperial?
No.
No. So this has been done on the arms of many volunteers. Before that, you have to give them you have to administer local anesthetic because it's highly painful. And my guru, Professor Tony Cass, has had it, and he said it's a lot of anesthetics that you have to give. I will show you one of the case studies wherein we've used these as a parallel, as a secondary way of tracking the biomarkers of interest, which is a classic example of therapeutic drug monitoring. But microdialysis, you can imagine, it's a painful thing. You can see a little bit of blood there as well, right? So it's clearly a bit kind of it's more invasive. Anybody here ready for? So I'm going to give you choices at the end of this slide, and then you can decide which one you would like to extract your skin interstitial fluid. Next one is suction blisters. As you can see, you basically create blisters there so that you can then analyze the blister fluid. Right? Does it look very friendly? All right. And the other option you have is your microneedles here. Now, apologies if the images put you off. This is this is basically porcine skin that we have on the screen. The reason we use porcine skin for research purposes is that's the closest skin that you get for human studies. So if you have if you have a research lab set up here, it's easy to get research ethics approvals for porcine skin and do testing on porcine skin, especially if you're looking at the mechanical properties, mechanical robustness of your microneedles and stuff like that. You can hardly see the microneedles here, right? I mean, these are microneedles which have been put and compare that to a hypodermic needle. Look at the length of this hypodermic needle, how deep it goes into the body. Right? So you have three different ways in which you can extract the skin interstitial fluid, or you can measure in the skin interstitial fluid: microdialysis, suction blisters, and microneedles. How many here would like to go for option 1? Nobody? Option 2? Option 3? I'd like to see the hands up a little bit more. So that tells me they're all awake. Yeah, option 3, everybody? Good. And that's what we're going to be talking about. So these are your subdermal wearable devices. The nice thing about the skin interstitial fluid, I mentioned the skin interstitial fluid is a treasure trove of biomarkers. You have different concentrations here. You have glucose, you have lactate, your stress hormone cortisol, lipids, ions, which I mentioned are going to be measured using potentiometric sensors, ion selective electrodes. And the nice thing here is, look at the concentrations here. You're looking at millimole concentrations, right? And the typical concentration range is 0 to 30 millimole. This is the concentrations in the body, and this is in the ISF, right? Look at the concentrations. And the nice thing here is not only do you find these target biomarkers, you also find them in concentrations that can be easily correlated to that in the blood as well. You know, there's a good correlation of glucose, for example, or lactate, for example, between skin interstitial fluid and blood. There may be a lag time. There may be a time when the blood glucose concentration goes up in the body. You see a peak going up, a postprandial peak going up first and then coming down, and the skin interstitial fluid showing a peak at a later stage. So there may be a lag time there of between 4 to 5 minutes, or maybe different. But then you can bring in your machine learning and AI tools to kind of account for all of this, and you can do your calibration accordingly. Right? So the nice thing here is, look at the concentrations. This is very good news for us, right? This is not a challenge for biosensing technologies. Biosensing technologies are more useful where you want to do ultra-sensitive detection. You want to look at biomarkers that are present but in very small concentrations. Drugs, micrograms, nanograms per milliliter. Biomarkers of Alzheimer's disease, I can tell you from, and we will have some lectures on that as well. We're looking at picogram per milliliter concentration. Right? How do you do those kind of, how do you achieve those kind of sensitivities? How do you achieve those kind of limit of detections? That will come through in these models. As I said, this is just an outline lecture to give you a flavor of what's going to be coming next. I mentioned to you about skin, it's a treasure trove of biomarker, and I mentioned about the two different theories which explain the presence of biomarkers in the skin interstitial fluid. One is the two compartment model here. As you can see, you have your subvascular plexus here, and through here you have your diffusion here. There's a continuous equilibrium going on between the subvascular plexus, which is your blood vessels, and your skin interstitial fluid. There's a continuous equilibration there, right? Goes up, comes down according to what's happening in the blood. The other theory that explains for certain biomarkers in the skin is your theory of what we call as the ectodermal origin layer. So this theory, according to this theory, during the human embryo, you have different layers. Everybody studied basic biology there. What are those 3 different layers? Ectoderm, mesoderm, and endoderm, right? So if you have, the skin is of ectodermal origin, meaning that the skin originates from the ectoderm of the outer layer of the human embryo. Any other organ that originates from the same layer would have the same kind of biomarkers. That's a theory. It's a hypothesis, still a hypothesis. I wouldn't say it's been fully confirmed, but that's a theory that has been, I mean, there are publications there. They talk about biomarkers like alpha-synuclein, which is a very valuable biomarker for Parkinson's disease. And people have started monitoring those biomarkers of alpha-synuclein or of Parkinson's in the skin compartment. Right? So if you can do that, if you can monitor things in the skin compartment, either using epidermal or subdermal variables, the advantage you have is you can do real-time continuous monitoring. And that then gives you a plethora of information. That gives you all the information that it gives you a whole profile, how the profile, you know, the direction, the duration, and the magnitude, you know, how the things change. You know, if you look at the profile of a healthy person, of how the glucose concentration changes, normally you would see 4 peaks. Each peak corresponding to the bolus event, right? Breakfast, lunch, maybe some snacks in the afternoon, and then maybe a heavy dinner. You know, the height will depend on what you've eaten, and your pancreas are working fine. Within 45 minutes, you see a peak, and that peak kind of disappears, or it starts to tail within like 2 hours. But if you look into a profile of a person with type 1 diabetes who has got no pancreatic function at all, I mean, that's really complicated. I mean, we've done some clinical studies, and you know, in the lab, and we've really seen it's all random. It's very hard to comprehend, and these people need more information rather than just getting this point information that you get from the top. You measured a point here. You do not know whether it's the start of a peak or it's the top of a peak, right? And the problem is people who are monitoring glucose, for managing diabetes using glucometers, they're measuring it in home conditions. They do the same routine every day. They're collecting a data point every day at the same point, every day at the same point, every day at the same point, every day at the same point. So there is no way you can actually get a full information on how the fluctuations are taking place during the entire day, right? So anything you can do in the skin to monitor your biomarkers is a good way of getting a real-time continuous monitoring device here. So this is a slide just to show you your different theories that have been proposed. This one has been confirmed. This one is still a hypothesis. People are still working on it, including my UK Japan project is on the same. We have mice models wherein we are expressing the human form of Alzheimer's, and we are trying to do a correlation study between the rat, the venous blood, the capillary blood, and the skin interstitial fluid. And we are using that to see if this model holds true or not, which is the theory of the model of ectodermal origin, right? So that's this one. Again, just to give you this is another slide to give you a comparison. Look at the comparison here. This is sodium in plasma, skin, and sweat, right? This is for you to make up your mind whether you would like to pursue the area of epidermal sensors, epidermal biosensors, or subdermal biosensors. Again, this and this are complementary. You should not judge. We are all scientists. We don't judge. We consider everything to be complementary. Things that the advantages of epidermal sensors cannot be realized through subdermal sensors. The advantages of a subdermal sensors cannot be realized through epidermal sensors. So there are pros and cons for both approaches. Choice is yours. So just to give you an example, sodium 135 to 145 millimoles in your plasma or in your blood. Skin ISF has got the same concentration. Sweat has got just over 10 millimole concentration. Still good enough for our biosensing devices, right? Potassium 39, that's a molecular weight, 3.5 to 5 millimole. Plasma skin ISF has got. So if you look at skin ISF here, most of them is very similar to that what you find. The concentrations are very similar to what you find in plasma. If you look in sweat, 1%. This one is plasma. Cortisol is similar to plasma. This is less than plasma, and this is very diluted. And this one again is millimole concentrations here. Right? Just a slide to give you an idea. Again, but look at here, cortisol, right? What value does cortisol monitoring give you? If it's easy to monitor cortisol in sweat, would you go for sweat or would you go for subdermal devices? A decision for you to make, right? You can think about it, right? That's the key thing here, right? And the skin ISF is more preferred. The reason I'm telling you why my inclination is towards subdermal devices is because subdermal devices are normally used with skin ISF, and in skin ISF the concentrations are, you can see, very similar to that seen in plasma. Okay? All right, I think getting closer to the time, but I think we are all okay. Everybody's still wide and awake?
Yeah, you can continue,
good.
No problem.
All right, let's have a look at some of the comparisons between ISF and sweat for biosensing. Sweat, easy to collect. However, the problem is it's variable and it can easily be cross-contaminated, right? You can have contamination with other things. Skin interstitial fluid is more stable. It reflects biochemistry, it reflects blood chemistry, and it's ideal for diagnostics. But trust me, when you start working on subdermal devices, getting the subdermal devices, because these are devices that are inserted, they're not implanted. Getting the devices to stick is a different problem, and we'll see that when I give you proper case studies, when I show you the poor animals. I had my students who went to do some experiments on the farm side to monitor glucose in cows. I didn't realize I'd sent them for doing the cow experiments on a Valentine's Day. So I saw them that to get the devices to stick, they were actually shaving off heart shapes on the poor cow, and then they were sticking the devices there. And then later on, when I saw the heart shapes, I realized they were made to do experiments on a cold Valentine's Day when they would have preferred being somewhere else. But the problem with wearable devices, with subdermal devices, is that can you have a device that can actually stick? Can you insert the device? Can you standardize the insertion without having to shave off the skin? Even in the human studies, we had to shave off the skin. I think the male volunteers were more comfortable with this. The female volunteers gave us a bit of a dirty look. Do we have to do this? Okay. Skin interstitial fluid is preferred for subdermal microneedle sensing platforms. I mean, that's something that's already made it. In terms of a bit of technology side of things, fabrication of materials, you can make these microneedles out of different technologies. Do we have facilities to make these here at NIT?
We actually we have some clean room facilities,
Okay.
and we also mostly rely on partners who
Fantastic.
do it for us. Yeah,
Fantastic.
they are more professional in and better.
You don't definitely need a clean room. You can start making them in, I'll show you examples. We've started using acupuncture needles, which are commercially available products, already got CE marking. So we'll show you how those things work. So you can use different materials here. You can use silicon, you can use polymers, you can use metals, you can use ceramics, you can also use stainless steel. I mean, the acupuncture needles are all stainless steel, much more robust. And the methods that you use, I already showed you the slide I showed you before. You can use micromolding, photolithography, 3D printing. The key design parameters is you need to look at the tip sharpness. If you have tip sharpness of about 20 microns, that's the key thing here. 20 microns is really good. That will not cause any skin inflammation. If you make it more blunt, then you can imagine it's going to cause some skin damage and inflammation there as well. The other thing you need to pay attention to is the spacing thing here. You need to make sure that they are nicely spaced. Right? There's enough literature there. There's enough modeling done as well on these. You don't want the bed of nails effect. You understand the bed of nails effect, wherein if you have a bed of nails, if a person can lie down on it, right? The person goes and lies down on it. The nail doesn't actually go through the skin, right? So that's called as the bed of nails. So the spacing is very important here as well. And then most important is the mechanical strength. You need to have microneedles which have got the necessary mechanical robustness, so that when you insert them and when you remove them, they do not dislodge. The microneedle doesn't, you don't leave anything inside under the skin. And then I'm going to be giving some, in the coming series we'll be talking about some of these, how as I said, you have the surface, how you coat them with a metal, how you functionalize them with your enzymes, how you functionalize them with your molecular recognition element. That's the important thing. We'll be looking into those, and we'll be looking into hydrogels which are biocompatible. And then I'll give you some examples of subdermal wearable sensors for livestock and human monitoring. And then we're going to have some lectures on AI as well, machine learning and things like that. All of this will come in the next few slides. This is some images I'm going to show you, which we'll be talking about as part of the case studies. This is the first human pilot studies, which was done back in 2013. As you can see, those were the days before my marathon days, so I'm a little bit more kind of stoutly built here. And that's the clinician there, and we managed to convince our clinician as the first participant. So that's a healthy participant we have there. You can see that the devices have been inserted on the forearm, and then we are using an IV cannula as the gold standard, and then we are doing a correlation study there. When you study a device, there are two parts of the study. One is tolerability. We spoke about the GlucoWatch, and we saw how the tolerability was really bad, and that's why the acceptability went down. So the first important thing about your medical device should be tolerable. So these are some devices. These are some examples to show you visual assessment. We'll do this case study, so I won't go much deep into this, but I just wanted to point out that this term tolerability is very, very important. So bear in mind that when you're developing devices, you have to look into tolerability of those devices. This is how the bioinstrumentation evolved. You can see the first studies that were done in 2013. We were using a trolley where our bioinstrumentation was sitting. We were mainly focusing on the biosensing side of things. Again, that's a picture of another, and this is how you normally represent pictures. You don't show the pictures of the participants there. The first participant happened to be a clinician, again, whom Khalid knows very well. Second one again was another colleague from bioengineering department with type 1 diabetes. Third one, no points for guessing this one. This is somebody doing studies in the home settings, which is very important to get your devices running. And the device I'm holding in my hand is a BIAP device, which Khalid was working on when we were at Imperial College. This is how our data looks like. When you actually get this is how the data is actually, right? Those of you who, you look at the traces here. So these are, you normally represent your data. This is a chronoamperometric plot. This is the current values you're getting, and you see the peaks here, and then you see what's happening here. And these stars are point measurements that are being done with venous blood measurements that are taken every hour or every half an hour. And this is where we are comparing our device performance of our device with CGM. You can see that we have a good correlation of the events that we have, showing that the device are performing as we need. Remember one thing: when you have your wearable sensors, you are not measuring glucose, you are measuring current. You have to then take that current and then correlate it to the glucose if the events are matching. And that's what we're going to be learning as part of the case studies as well. So as I said, I'm giving you a summary of 15 years of my experience, and I would like you to build on that and take it forward and see how far you can take it. Again, this is how you represent the performance of your device. This is what we call as a Clark grid error. Right? In this, you have the different zones here. You have this thin line here. What you're doing is you're correlating the performance of your sensor against a gold standard here. You try to be as close to that line as possible. But in the case of glucose, you have different zones. You have zone A, and then you have zone B here, and then you have zone C's and zones D. If your values fall in zone A, if all of them fall in zone A, fantastic. Your you're destined to become a millionaire. If not, don't worry, you can work hard again and try to get these values which are in zones B and zone C to again start falling. You go back and re-optimize the device, you still have a chance to become a millionaire there, okay, or a billionaire, whatever you want to become. And these are some pictures of some human studies which I will be presenting. I think in the interest of time, I'm just going to quickly scroll through just show you exactly how the devices now are. Now you have these platinum microneedle based devices which are mounted on a PCB electrode, and how we use this for measuring glucose and lactate. This is some data here. This is where we saw that I showed you the data before, the raw data. Look here, this is how you get the data. This raw data sometimes doesn't make any sense. I mean, this is all smooth graphs. You see, look at this data here. This is what the lactate, this is how noisy the data is. To make sense of this data, if you bring in the AI models, it works much better, and then you can get a much better correlation as well, and much better assessment of your performance as well. And that's to show you this particular device here, where these are the 3-day studies that have been done: day 1, day 2, day 3. This is measurement of the lactate when somebody is running, cycling, and again cycling. You can see the different lactate levels there. These are Clark grid errors. You use the Clark grid errors for looking at the performance of your glucose sensors, and you use what is called as a Bland-Altman plot. This plot is normally used to look at the performance of your this thing here. The important thing is this line here. If you haven't understood this, don't worry, all of this is going to come. We're going to have plenty of examples, plenty of case studies, and we're going to discuss very fine nitty-gritties and everything related to these studies here. I think this probably, and we've also done some animal studies, as I mentioned. This is the animal studies. I mean, if you go to a farm in the UK, it's not that you don't have point of care devices, you have these point of care devices. You can see this is a strip that's been used for measuring ketones in cows. But the painful thing here is, can you get capillary blood out of cows? No. Why? Hooves, right? The animals, I mean, and the environment is horrible. I mean, it's very contaminated. There's feces all over the place. Even the belly of the cow, you see traces of feces here. The legs are almost, half the leg is covered in feces. The udder is covered in feces. So where do you monitor then, right? If you were to go and work, help the farmers with monitoring well-being of their cows, how do you monitor that? In the UK, we have large cow farms, so we would like to have everything monitored centrally using a robotic system. So I'm going to be doing case studies on the animal studies as well. This is how you extract blood. You're taking out venous blood from the tail of a cow, which is, I don't know how it's done. And this gentleman, he's one of my collaborators. He happens to be a veterinary doctor, right? It's not done by the farm workers. It has to be done by a specialized person. So therefore, you have different challenges there, which we'll be seeing. We've developed our own devices there, and then we've done some studies. Just to show you these, I'm going to run this past. Just to show you this video, that's similar to a heart-shaped thing that's been done by the students there. This is an applicator to standardize insertion, and he's used the applicator, inserted the device, and takes it off, and the device is sticking there. But see, look at the thick hair you have here. I mean, it goes under the collar of the cow. That's your device there, just to show you this. So the challenges that you have here, sensor drift, sensor noise in electrochemical sensors is a nightmare, right? Now we have machine learning, now we have AI, but 10 years back, or 2010, we weren't looking into those kind of things, right? So we definitely need a lot more machine learning, a lot more AI there to address the problems of sensor drift, sensor noise, and biofouling. We have very limited long-term data, and there are a lot of regulatory hurdles here. The next step is to bring in the AI, multiplex sensing, and when I say multiplex sensing, not only measure glucose, also measure glucose, lactate, and also measure maybe a third analyte there as well, right? The more analytes you and then build clinical decision systems based on that. I think that's something we'll be discussing here again. So basically, this brings us to the summary slide. With me running late by 10 minutes, but I don't mind. I think we're having a good, and none of you have fallen asleep. That's a good sign for me. So summary, wearable sensors are reshaping continuous health monitoring devices. Microneedle patches, also called as subdermal patches, show great promise for ISF analysis. Not that Epidermal do not. We have some good examples for those as well. Challenges remain, but then we have this wonderful audience here, which are now ready to learn from this workshop and make rapid progress, which will be underway soon. With that, I think I'll end my talk, and I'll open the floor for any questions that you may have. There's a microphone, so please use the microphone so that the questions are clear to me.
Yeah. Any questions, please? Any?
Remember, no questions are stupid questions, right? Questions are questions. So, any questions that you
Please
have,
feel free to ask. No worries.
and I do appreciate this is just the first lecture. There's more coming on case studies, and things will become much more clearer when we discuss them on individual case studies.
So what we have covered is a very nice summary of the state of the art. We have also looked at the skin anatomy. So if we are making some devices, wearable devices, subdermal devices, then what sort of skin anatomy? It starts all from the anatomy and the biology. So we need to understand. So we have got a very good overview there. We also looked at the biofluid extraction methods. So which, as we saw that this microneedle approach is probably the best and the most comfortable one for the patients or the users.
I would keep it safe and say complementary.
Complementary, yeah.
I don't want to upset Joe Wang and John Rogers, people who work in this area of epidermal microfluidics.
So I just have few questions.
Yes, please.
So when we do microdialysis,
Yeah.
what are the challenges in terms of why is it so painful? Is it because of we are touching the nerve endings, or
You are going, it's much more invasive.
it's much
As I said, as we saw from the poll we had,
yeah.
nobody was ready for a microdialysis.
Yeah.
I mean, you will be looking for volunteers tomorrow, right, for your clinical studies. So
No.
I couldn't find any volunteer in the audience here who would be ready for microdialysis. It's very, very invasive. As I said, you can see traces of blood there as well, and you have to give it with a local anesthetic, which means that it's definitely going very, very close, or at least touching the nerve endings.
So this microdialysis is for extracting ISF.
Microdialysis is a secondary standard thing,
yeah.
you know, so what happens is when you're doing these studies, you need to extract skin interstitial fluid and then do some really measurements in the lab. You need to do you need to do some mass spectrometry and things to identify, exactly and get a good reference there. So microdialysis, we use microdialysis in some of our studies for that purposes.
Great. And can you elaborate a little more on the model of ectodermal origin? So what sort of
that's again a
thesis is
hypothesis
behind,
that has
yeah.
come out of some studies that were published from New Mexico University and what they've said there is that there's a good correlation. In fact, there were some good articles even on the BBC where they said there's a good correlation between biomarkers that are normally derived from the same origin in embryo. So if you have the skin is derived from the ectoderm of the embryo. If you have, and the brain and the spinal cord also seems to be derived from the same. So you would find the same distribution of nerves in the brain, although it will be denser, much more denser, much more thicker in the brain. But you would, because when you're looking at neurodegenerative disorders, you're looking at biomarkers related to that. So you would have the same biomarkers, but you may have it at different concentrations, and they may appear at a different time. Okay. But the concentrations you would expect, because sometimes it's very hard to explain how can a biomarker like alpha-synuclein originate in the skin. I mean,
exactly.
Because if you look at it, it's basically diffusion of the biomarkers from your venous blood, arterial blood, capillary blood, through the subvascular plexus into the skin interstitial fluid. And diffusion, as we all know, is much more faster when the molecules are small in size. They diffuse faster.
Yeah.
Larger molecules are normally stuck at the barriers. Now, how do you explain large hormones, which are large molecules? How do you explain alpha-synuclein? Metabolites, easy peasy. Glucose, small molecule.
Size.
That's all being produced and they've been dumped there. They also have some coming through the sweat as well, through the sweat glands. How do you explain the larger molecules? For that, there was this ectodermal theory.
Right.
Ectodermal origin theory.
Yeah, I think it can lead to a new discovery of
absolutely. I mean, that's why skin is turning out to be a very useful sample matrix, skin interstitial fluid.
Great.
And that's why I fondly call it a treasure trove of biomarkers.
So when we talk about tolerability, what exactly do you mean in terms of, is it in terms of pain or in terms of what exactly?
So the slide I showed you, I'm sorry I had to rush through that because we were running a little bit of this thing time. The slides I showed you here, if you remember this slide here. This one.
Yeah.
This is basically when you insert the device,
right.
And you've worn it for 24 hours. So you're looking at after 24 hours, you remove it, you get these marks here, right? And these marks disappear depending on the color of skin.
Right.
In fairer skins, they stay a bit longer. In darker skins, they disappear much faster. Now, if this was causing some form of an inflammation, like we looked at the example of GlucoWatch, where the adhesive was causing a real bad rash. Imagine you wear your device and it gives you a rash.
Yep.
Right? So imagine it giving you an infection or giving you a crack or something like that. So that's what we call as tolerability. How
Right.
well is it going to be tolerated by the person who is wearing them, because it's a wearable sensor.
Yes, and whether it is leading to like triggering any adverse kind of reaction or allergic reaction.
Exactly.
Yeah. Yes. Yeah.
You see, most of the wearable devices are designed in such a way that, and they're designed in a format that is much more easily acceptable to us.
Yeah.
So, for example, watches, because we are used to wearing watches.
Yes.
Try to make something which goes somewhere else.
Yeah.
Yeah, okay, ears we can say, because people are used to, especially ladies are used to wearing earrings.
Earrings.
But imagine something for a man. Try to make a device which goes sits on your nose.
Yeah.
I don't think it will be tolerated, right?
Yeah,
So
absolutely.
it comes, and this is how you find out about tolerability. It's you do this, what we, as mentioned, we do a public patient public involvement exercise there. Oh, I'm developing a continuous monitoring device, but that's going to sit on your nostril. No.
So there is a, I mean, if we are developing medical devices, there is a requirement of looking at the basic biology
Acceptance.
and then moving on to device and then moving on to design as well, so that there is more of an
Yeah,
acceptability.
I think these have to be done in parallel. They have to be done simultaneously,
Yes,
because you
yes,
may
yes,
come
yes,
up with a technology which works fantastic,
Yeah.
and if there's no volunteers, like let's say microdialysis, fantastic technology. How many people are ready for it? Nobody.
None. Yeah.
That's why these things have to be. So in the UK, we have this culture wherein when we give a Gantt chart, we say validation of devices, PPI group meetings, looking at the acceptability right at the start.
Great.
You don't want to be making something like the Google, lens,
Yeah.
and then finding out that there's no takers for it
Right. Yeah. Absolutely. So it has to start right at the beginning
right at the
when
start.
you are developing starting a project, kicking
Exactly.
off, so that you can think of how to integrate many things in a small form factor in a wearable device sort of form. But quite nice actually. It's very useful to know. And this 20 micron thickness, that
Yeah.
tip sharpness,
Yeah.
that's the sort of
That
standard.
comes from a paper that was published, I think it was a paper that came out of the Netherlands, I think one of the institutes in Netherlands, where they said that anything above, ideal dimensions for the tip sharpness, which is, I mean, it's for animal studies, but still, here, this tip sharpness that you have here, this has to be
20
around 20 micrometers. If you have it 20 micrometers, it causes less inflammation and less damage. Anything less than that can break or dislodge.
Okay.
Anything more than that can cause more damage to the skin.
Okay, that's quite useful to know. If you are making microneedles, then you can. This is
Aim
part
for
of
20
your
microns. You may end up getting 25, 30. It's not going to be the end of the world,
Yeah,
but this is considered to be the
standard.
top
Top.
bar.
Great, good to know. And just if we go to the device comparison where you have these plots, I just wanted to ask a few things there. Yeah, if you move forward.
This one?
No, next one. Where you have the CGM and plus, yeah, right, this one. So what I found quite interesting here is, if you look at the peaks, the pink, which is the Dexcom CGM sensor,
Yeah.
it looks like there is some sort of a delay or in some
Yes.
sort of a filter kind of response there.
All the
It's,
sensors have got what we call as warm-up time. So even,
Warm-up.
I don't know if anybody has used a CGM sensor here.
Yeah,
A CGM sensor, as soon as you implant the sensor, again, be careful, I'm using two terms here. Implant and subdermal is insert. When you implant a CGM sensor and it comes with an applicator, they do not switch it on for the first 1 hour.
Yeah,
It
1
stays quiet for 1 hour. They wait for the sensor to equilibrate. I mean, the reason I have understood that is when a sensor goes into the skin interstitial fluid, the fluid is not like a continuous flow. This thing, it's in the form of droplets. I think all these droplets kind of go together around the sensor surface, and then they all kind of
form a
coalesce.
layer. Yeah. Okay, nice.
They kind of aggregate.
Yeah.
And they form a continuous layer, and then it starts. So that's what we call a sensor warm-up time.
Right.
And plus the other thing is also with electrochemical sensors, when you start, you always have this drift. It goes from high current value, it starts to go towards a low, towards a
Yes,
background
yeah.
thing.
So
That's-
this continuous in the plot here, it seems to go a little bit up. Is that because of drift or?
That's sensor drift.
That's-
These are examples of drift.
Yeah.
This is where you have a sensor warm-up time. Again, these guys are also going up
Yes. Yeah.
with this.
Yeah.
And then they're starting to monitor peaks here. So you see these are see what I said. We are measuring current.
Yes.
We are not measuring glucose. These guys,
Directly they are giving.
they
you the
have
glucose.
given, because these guys, they have, Dexcom was the first company that actually spent a lot of money optimizing their software.
Right.
They stopped working on the technology side of things and they started using more machine learning and AI in 2010, 2012. Sorry, in 2015 onwards.
Quite early.
And they've done a lot of investment there. And I think they had the first perfect software.
Yeah, they have the best MARD, I guess, the mean absolute relative difference.
Again, I don't want to claim that, and then I don't want to claim that.
Okay.
And go into a dispute.
Yeah,
Otherwise, the Abbott guys will run after me and say, oh, "How can you claim that?" So again, as I said, for me, all technologies have got their pros and cons. But yes, I mean, when I was at Imperial, I had the chance to use Dexcom because we had a collaboration with them. At Swansea and Liverpool, we are using Abbott because we have a collaboration with them.
Yeah. So here for our studies also we use Abbott mostly.
Yeah.
Because Dexcom is not available here, and
yeah, I think you use them as a secondary reference.
Exactly.
Your main reference is this guy here, which is your CG, your venous blood.
Yeah.
I think you're covering somebody behind you.
So yeah, any more questions for this session? So it's more of an overview kind of session.
So I just want to know, like, is CGM sensor, like, can we call CGM sensor minimally invasive sensor or subdermal? Because just
no, it's not. It's subcutaneous.
Subcutaneous.
I don't want to fall into that whole idea of that debate on definitions.
It's an implantable device. So
absolutely right. You've answered it yourself. So you can call it whatever. So there's a difference between implantable and insertable devices.
Okay.
So CGM sensors, you can wear them, but they are implanted and they're subcutaneous. You can also wear a heart assist device, right? Because you're wearing them inside your body, but those are implanted. So you cannot call them minimally invasive or non-invasive.
Yeah.
For me, the definition of a wearable one is something which is either minimally invasive or non-invasive. Okay. Epidermal, non-invasive. Subdermal, minimally invasive.
Yes.
You will find a few people who work on microneedles also calling them as non-invasive.
Yes, I have heard like many terms, minimally invasive.
Minimally invasive is I think this was introduced by us and by Ryan Donnelly from Belfast.
Thank you, sir.
No, Ryan Donnelly is Queen's. Tyndall is Connor Mahoney.
Oh yes.
Yes, please.
Yeah, just 1 minute. So if you speak in the mic, it's recorded also.
So, So this is Priyanka Thakur. I would like to, can you simplify the word chronoamperometry?
Chronoamperometry. Chrono with time, amperometry, measurement of current. So when you measure current with time, that's called as chronoamperometry.
Thank you.
If this is not clear, we're going to have, I think in the afternoon session we will have we'll have slides on the basics. So don't worry about it.
Thank you.
No worries. Yes, please.
Sir, my name is Satya. I have some basic
Sorry,
questions.
I didn't get your name.
Satya.
Satya, yes.
Sir, I have some basic question like from chemistry point of view.
Yeah.
So whenever we're like reducing something, we have to choose a particular reduction potential.
Yeah.
For cortisol, I hope the reduction potential minus 1 volt, and like for dopamine it's 1 volt. It's like 2 volt difference.
Yeah.
Whenever we are going for amperometric case, so we have a electrode, and electrodes are basically defined with their surface area. And whenever we have a surface area, we get a background current. Now, if you are modifying a surface area in such a way that it's suppose you are telling like we are modifying with a 3D printing. So in that case, I hope the surface area is getting increased. So whether the background current is also increased or it's getting same as that of.
It's a very good question that you've asked me. So it depends on the material that you're using as a surface for your surface. The material, if it's gold, of course you're getting a very high background current. But if you can use materials which are more catalytic in nature, like platinum. With platinum, you can get low background current. So with a careful choice of materials, you can kind of play around with the background currents. But it's very important that you control your background currents, because if you get very high background currents, then you're actually affecting your sensitivity. We will have we will be covering this aspect as well in the afternoon session on when we cover the basics.
So, sir, my second question is, whenever we are targeting a molecule, we just need, like we are telling it's a sensor. That means it's particular to that particular, molecule.
Specific, yes.
Specific to the molecule. So, I have just a small, question, like how it can be sensible. Means whether we are using the particular enzyme. Suppose we are not, we have thousands of molecules, we don't know what are the enzymes, specific enzymes for them. Then in those cases, what we can use?
If you wait, if you are a little bit patient, I will be giving you very good examples of the different kinds of bioreceptors. You've got a very, very good question. It's just that you're a little bit eager right now. The thing is, I'm holding a lot of students from their lunch. And if I start answering this, it's going to go on and on. So what you can do is, during lunchtime, come and see me. We can let it go as far as you want, as long as I don't answer. Don't leave me till you don't get all your questions answered. But for the moment, I would just ask you to hold on to your horses. After lunch, the next part is mainly on looking into the basic mechanisms. You've got a very valid, very, very curious question there, and I really appreciate that. But it's something for which I cannot answer within the next 30 seconds or 1 minute.
Absolutely. So we have actually a lecture session for bioreceptors. That time you can see more how to make it. I guess you are asking about how to increase the specificity of the sensor. So you can have a look at that time as well, or you can talk to sir, like he said, after lunch or during lunch. Any more questions? Yeah, please. You can ask anything. So the like basics about chronoamperometry, and all these electrochemical techniques we will be covering in the next lecture, actually in the afternoon. Any more questions? Pragyan.
Hello sir, I'm Pragyan, PhD scholar here. My question is, while using microneedles, obviously we're going to the subcutaneous layer and taking up the ISF that is present. Subdermal layer, and I am taking up the ISF. Now, if the environment changes, let's say we are in southern part of India or maybe eastern part of, let's say Odisha, the temperature is very high, around 45 degree. So people here sweat a lot. So whenever the sampling is happening through the microneedles, is there a chance of contamination between ISF and the sweat? And if there is, then how do we segregate both the parts?
Very good question. So to answer your question, you see these devices here, right? So the dots that you see here, these are the microneedles or microneedle structures there. So the base that we have here, that's also part of the case studies that we have. We normally cover the base with an insulating material, so that we are only measuring, again, the needles that you have here, these are solid microneedles. We are only measuring what it comes under the skin. So if I push it into the skin, and if this is how I represent my microneedle, and this is your skin, this is where your sweat is going to be. My needle has been, and what I would normally do is I would cover the base, so that I'm only measuring what is around this particular surface here, nothing that's on the surface. And the base has been insulated, so it doesn't matter if there is sweat here.
But sir, if that's a porous material, then the contamination chances are high, right? If the needle is made up of porous materials.
Yes, if the needle is made up of porous material, but don't forget, the needle first of all is, okay, I'm talking about solid microneedles. If the needle is covered with a layer of metal and then functionalized, and then on top of that you have a polyphenol layer, then there's nothing that can actually ooze out through the needles or into the needles, right? And we are sitting in the subdermal space and doing measurements there. We are not extracting anything out. We are not pulling the interstitial fluid out. People have done it. What you say has been done by Joe Wang, wherein he's taken a hypodermic needle-like structure. He's got a lumen here, and he's extracted, he's got his needles in this format, which look like this, bevel shaped, and he's extracted interstitial fluid, and he's measured things in the lumen of the interstitial fluid. You can do that as well, right? And your question is a very good question, because some people are actually using the combined approach of measuring in the skin ISF and sweat. But again, because there's a huge variation there, you need people like Professor Khaled and Professor Prasun who can bring in the machine learning and the AI to help you standardize and create a system there. Model these and create a system there.
Thank you.
So just for the benefit of our participants, it would be good to mention when we say subcutaneous and subdermal, what is the distinction? Just to-
Subcutaneous is, so I think for that, let's have a look at this one. Can you see where subcutaneous tissue is?
Yes. Yeah.
Can you see where the subdermis is, where the space between the epidermis? So microneedles would sit in here. That's why I was trying to show you in that image. Injections could be subcutaneous.
Okay.
So if you have a device which is subcutaneous, if you're looking the sensors that are commercially available, CGM sensors, they will go all the way deep in, sit in here,
Yes. Yeah.
right? And we are measuring here, just below the epidermis, in the dermis. That's why we call them as subdermal.
It's actually a nice specification, because when you say minimally invasive, some people also refer to CGM as minimally invasive. But where do you distinguish between?
CGM is technically it's not minimally
technically,
invasive,
yeah.
but as I
So
said,
bec-
I don't want to
just,
ruffle
yeah,
feathers of
yeah.
people who claim it to be. As I said, I mean, if you look at this microanatomy here, you see this is your blood vessels here, right?
Yeah.
So anything that goes below here, and in fact, people who use CGM, sometimes I myself have used CGM many times. You've used it,
Yes.
and when you pull it out, when you dislodge it, you see some blood.
Little bit of blood coming.
You see
out.
some capillary blood there, and your nerves are also here in this area. Sometimes you even feel a tingling sensation with the CGM sensors.
And I mean, in subdermal devices, you would not touch, or you would not.
No,
get
subdermal
blood-
devices
blood
sitting
you
here.
would not
Until and unless you really push them very hard, and until and unless your skin doesn't become too floppy and too skin this thing. I don't unless if you're not causing any damage, it doesn't say. So look here, this here image. Actually, I should have mentioned this here. This is meant to be a CGM sensor. Look, this is where it goes.
Yep.
This one,
Yeah.
and this is where the microneedle goes.
So how do you insert the microneedle? So just a
I
small
showed you a video.
press, or so your array, like microneedle array, how do you insert it? Like just a small
Applicator. You use an applicator to stand. I showed you the picture of with the. You remember the picture with the cow?
Yes, sir.
That's where you
Okay,
were.
okay.
That's an applicator. This is an applicator. So you have your device. So this is the bioinstrumentation. These are the needles which have been functionalized. They sit on top of this.
So how much force does it require?
10 newtons at a speed of 10 millimeters per second. That is very, very important.
Thank you, sir.
And it's a spring-loaded applicator. Anybody can design it. If you have a 3D printer, you can design these. I mean, my PhD student is designing these in the lab using his 3D printer. It's easy.
Sir, my name is Shayantan and I am a MTech student. So the question is that you already discussed that we can use the epidermal microneedles on the surface of our skin, but
Oh, hold on. I think we are bringing in two different. Epidermal is not microneedles.
no sir, actually we are discussing about the microneedles which can be introduced on the skin, so that we can cure some damages or like
Diseases,
stuff.
yeah. But those would be subdermal. They wouldn't be epidermal.
Sir, but I am discussing about the epidermal.
Okay.
So in this case, there are different parts of our body. So the stretch or the strain can be different in various parts of the body, and it is also different. Like if you are using the microneedles in our hands and on the legs, it is a more movable part, and there is more tension, and also it can prone to the physical damage also.
Yeah.
So if there is so what is the distinguishable parameter so that we can use these microneedles in the hands and on the part of head which is not more physically damage prone area?
I will
So-
turn this question around to you.
Okay.
I'm giving you the post of a product design specialist who has to design an epidermal sensor.
Okay.
Which part of the body would you design it for?
So if we design the epidermal microneedles, which is
Hold
using
on. Just epidermal. Let's stick to epidermal.
okay, and then is in hand and
So you
and
design it for the hand?
yes,
For which specific part of the hand?
The arm or in the
Arm. So you're expecting a band? Or full
yes,
band?
yes, sir.
What about finger?
We can also use in the finger.
No, you're the product manager. So you need to
Okay.
give me one product.
Okay.
Are you giving me a finger ring or are you giving me an armband?
On one armband.
You want to give me an armband? That will be more expensive than a finger ring.
Yes. Yes.
So what I'm trying to say here is, without being, what I'm trying to say here is cost is a very important factor that you have to take into consideration when you're designing the devices.
But
You want the devices to be affordable.
Okay.
If you make something which is in the form of an armband, it will be much more expensive to make and sell and afford. If you make something in the form of a tiny little ring finger which can do the same job, because at the end of the day you're measuring concentration, you're not measuring
Yes.
volumes.
Yes.
So it doesn't matter how big your sensor is, right? You can measure that same thing with a small
Yes,
surface area.
yes,
So
yes.
you design something. So cost is a very important factor, and it's good you brought up this question, and this is how I'm going to answer it. Is it will depend on.
And sir, also on another question is that this region is more prone to physical damage because it is using in our hand. So we should need some optimization so that this device can be endure that kind of physical damages also. So
Well,
that
Normally, the design engineer, whoever designs a device, does take into account all the factors.
okay, sir.
Right? For example, when we started working on our devices, subdermal devices, we thought which would be the best part. We started using a forearm
Yes.
because it was easy for us to stick something here because you have a much surface area here.
Yes.
And then in the next studies, we started using the back of the arm because
Okay.
we were having CGM sensors. They were sitting on one side of one arm. We said, let's have the other one sitting exactly in the same location, same anatomical location.
Okay.
Humans is easier because
Okay.
you can do some studies. It's the
So-
animal part which is really hard.
So the site is also specified, but that means we cannot use anywhere in our body that type of devices.
It depends on what device you're making.
Okay.
See, I can give you, for example, in the animals. One of my preferred site in the animals, especially in cows, is udders because the udder is highly vascularized.
Okay.
And I have a feeling that if we manage to tap into the udder, we can actually pick up even infection
Okay.
because it's highly vascularized. You are actually, in the skin interstitial fluid is very much in where you can see there's very much in close contact with the subvascular plexus there.
Okay. Okay.
But again, as I said, this is something that depends on the type of application. What are you designing it for? Imagine, is it easier to wear a ring and go for a run, or is it easier to wear an armband and go for a run? This is a personal choice.
Okay. Yes, sir. Thank you, sir.
So, any more questions?
Yes. Yes, please.
Use the mic.
you have been using for the last 15 years. So what is the regulatory aspect related to it? Because before it is getting translated, we need to understand that these are some sort of the insertable device or just a patch sort of the device. So what is the regulatory in the UK?
In the
regarding
UK,
it?
it's straightforward. It's a medical device.
Okay.
And I think it falls in class 2.
Class 2.
Yeah,
Okay.
I think it falls in class 2, if I'm not wrong. I need to go and check one more time. And I think we had to appear in front of a research ethics committee as well.
Okay.
We haven't gone and sought huge amount of regulatory approvals from the MHRA, but
Okay.
we have definitely got all the required research ethics commission permission. I think we are still waiting for the whole, you have to get through multiple stages of human studies to then get to a stage where you start getting CE marking and MHRA approvals
Okay.
and stuff like that. But we have approvals from both MHRA as well as the research ethics committee.
Okay. So when
It's
you
a medical
use,
device.
So when you use these sort of the insertable devices, have you noticed any inflammation over a prolonged period of the time, or how long it has been inserted for a certain application?
We've done 3-day studies.
3 days is okay.
With 3 days, we've seen there is biofouling, which affects the performance of the device.
Okay.
There have been cases of adverse reaction as well in some people,
Okay.
but that depends on the nature of the skin.
Okay. Okay.
It also depends on the person as well. But by and large, they are very safe.
Okay.
So just also to add to this, our digital twin is the microneedle device that's used for therapeutic drug delivery.
Okay. Mhm.
So we are following them to see exactly how they're getting the regulatory approvals.
Okay.
So this is also the opportunity to tell the students about digital twin as well, which I think you
Yeah.
can explain better.
Okay. Thank you.
So, any more questions? Otherwise, we'll close off this session. No. Okay, thank you very much. Thank you, Professor Sanjeev,
Thank you.
for the nice session. Okay, audio off now?